Then you have it.
Okay, so are there any questions? How are those homework assignments working out for you? Hard?
Hard.
Good.
Way
Good.
too many.
Who wants to help study with me?
There we go. Anyone still waitlisted? Are you sure?
I haven't actually checked.
I'm pretty sure you were in.
Yay!
Let's check after class. I think I saw your name. As in, well, do you have access to our course on campus? Do you know? When was the last
I
time you
don't
were?
know. I haven't checked yet.
That's another way to tell. If you log in and you see this class on campus, then you're in.
Okay. Well, I hope I am, because they already dropped me from the other one, so.
They did?
Yeah, they did as soon as I talked to you. They're like, oh, we'll just go ahead and drop it.
You. So homework questions. How is that hard assignment or assignments?
Our first quiz is due on Wednesday, and we have 2 homework questions.
Wait, isn't I thought it was due on Sunday?
Oh, is it
I'm pretty sure it's due on me.
Yeah.
Yeah.
like this Sunday?
Yeah, I know.
I think that those
I'm not
are,
ready.
I think those are the due dates. So let's go back and see.
Is there a certain time it has to be?
I think by midnight, our
I don't learn from computers.
what?
Like, I feel like a lot of it, I don't really remember, and we didn't really talk about it in class, so it's really hard for me to learn.
Well, you have to talk to me in office hours. Go to the tutoring lab.
Okay.
This is
Well, I
the
went
correct-
to the tutor.
These are the prerequisite materials. Stuff that you know in your sleep.
No, I don't.
Well, then, you
1.1
then we have
1.4.
bigger issues. Because homework 0 and probably homework 1 are 2 of the easiest assignments that we'll have this semester. So look, quiz 1, yeah, it's due on September 8th, which is, I believe,
Sunday.
Sunday. Now, are there any specific?
At midnight?
This section,
Pretty sure.
or section 1.1 to 1.4 is still like stuff we should already know.
Yeah, it's basically, the book kind of really slow at getting going, so it just talks about slope for the first, like, 4 sections. There's nothing deeper. I think there are 3 sections that just talk about slope of the line.
Okay.
In different angles and perspectives, but it's all the same thing. So we're mountain time, yes, 11:59, so by midnight on Sunday. So that's the first quiz.
I have a question.
Yeah,
Is the first quiz on the prerequisite material too, or just the first chapter?
first chapter, so it covers 1.1 through 1.4.
But you have to do the prerequisite to get to the
Yeah,
next.
I'm that kind of an Because look, this is the setup. You see homework 0. In order for you to get to homework 1, let's see, homework 1 will say you gotta get like a 70% on homework 0. So you get 70% on homework 0, homework 1 opens up. And when you do homework 1, you'll have to get 80% on homework 1 before quiz 1 opens up. That's when you only can take quiz 1. Yes.
How long are the homeworks open? Only till we take the quiz? Like, because right now I have not finished homework 1, or 0, but I started 1. So can
that
I
means-
always go back and like go through?
Yeah, the homework will stay open for a while. I mean, there's no due dates on the homework. You'll be able to go back and rework them, but the due dates are on the quiz. And you see, basically starting on the 8th, we'll just go 8th, 15th, 22nd. So basically due on Sundays. Yeah. Now the thing, so quiz is the only thing that goes into your grade, and you do have 2 shots at that. So with the highest scores counting. Let's see what happens homework 2. How is that set?
And the computer grades us, like you don't look at our work or anything?
If you want me to, I can. If you disagree with the computer, because a lot of times you feel like you put the right answer, but you know. And I think I
Yeah.
told you guys that there sometimes it gets a little iffy, but it's better now. It used to be really good.
Okay.
Actually, it's pretty good now.
it's not too bad, but like sometimes I've just like didn't reduce one thing or something. And, like,
Oh, you have to reduce whole thing. Yeah, that's, I would mark you wrong as well if you reduce. We have Melanie. How's Melanie doing? Can you hear us?
Just get a new mic.
No, not the new mic, but I have a whole new software sharing thing that we're
Can you-
using.
Is there a way for us to access the notes that you take and like?
Yeah, they're all on campus.
Okay.
So if we miss class, can we go on to that?
Yeah, if you miss a class, let me show you. Here's our, so what section? You guys, O3 section. So if you go to O3 section, modules, click on modules. Let's see what's there. So there is a lecture from Monday, last week. I haven't posted lecture from Wednesday.
Is that just like a recording of
Yeah.
the class?
And I'll probably be adding lecture notes. So Melanie, can you hear us? I'm gonna mute Melanie. I may have to move closer to the mic. Oh, and I have to click top button. That's not. Here we go. Now it's better. Melanie, can you hear us? That's better. You can type in your answer if you can, and if you're gonna start typing, then we know that you can. Okay, she's typing. She can hear us. Okay, good. Yay, we're in business. So yeah, because this is better than what we had before. That's what we used to have back in the good old days. So I'm going to start sharing my desktop. So I'm sharing my desktop with you, and yeah, if you have a question, you can do this little hand thingy. We'll be able to hear you, I think. Okay. All right. So any math questions? Yes.
So since all the stuff's online, it's always open notes. It's like always open notes. Like we won't have anything in class where it's.
Well, no, we'll have exams in class.
Okay.
Yeah.
Which is no notes at all.
Yeah, no
Ever.
notes, only exams.
Okay.
But at home, you can just, just like any other homework, you just do whatever. And basically, the whole difference between doing a homework assignment, you have those extra learning tools that come with that My Math Lab, where you can ask questions and things like that. Just on the quizzes, they're taken away from you. You kind of have to get a little more creative on the quizzes. Same problems, but none of that ask your instructor, help me solve this options. Okay? So any math questions? How's the homework?
I spent 8 hours on it so far.
Oh, it's nothing. You should have spent 8 hours on day
Okay.
one.
It just seems like
Yeah, it's everything you've ever learned in math, and that one homework zero
I
is
just feel
huge.
like discouraged.
That's all right. It'll get better. Hopefully. I mean, we'll definitely slow down after a while. We'll slow down after a while. So we introduced functions last week. Okay, so we talked about basic definition of a function, and we also talked about, let me do one more thing. Am I recording this thing? So we have the basic definition of a function, what it means to be a function. Remember that whole no repetition in the x. You cannot have one x value corresponding to two y values, and Shaq was a good example to that. Remember that? Oh no, you left. So remember we used him as an example? Okay, good. Watch the video. You were our learning tool. So example, if I just write something, a set of ordered pairs, let's say A, and it's 1, 1, 2, 1, 3, 1, 0, 0. So that is a relation. Is this relation a function? Yes. You just look at the x values. If there is no repetition in the x, you catch yourself a function. Y doesn't matter. Okay, so the fact that we have 1 goes to 1, 2 goes to 1, 3 goes to 1, that's okay. It's still a function. All right? So yes, a function. And the reason for it, you can just say no partition in the x. Okay, so we don't want to have same x values going to two different y values. But two different x values going to the same y value is okay. All right, good. I'm not sure what that sounds. Okay, good. Now, so of course, we will be looking at functions in a more algebraic sense, like for example, y equals x squared. So we can say that y is a function of x here, because this is, again, this is a relation, set of ordered pairs. For every x you do get little y. We can plot this relation, right? The way we graph things, you probably remember, we just generate a whole bunch of values, right? We just plug a whole bunch of x values, let's say -3, -2, -1, 0, 1, 2, 3. So if x is any one of those, you plug them in here, you get your y values, right? So if x is -3, what is y? 9, right? You plug -3 in for x, -3 squared equals 9. And then you get 4, and a 1, and a 0, and a 1, 4, and a 9. Right? Set of ordered pairs. And if I go ahead and I plot this ordered pairs, go ahead.
Wouldn't that be y then x? No.
I'm sorry, what?
The chart, wouldn't the first one be y
Uh,
value, and then x squared would be.
yeah, so well, because y equals x squared. So I'm taking whatever the x is,
Okay,
plug it in
sorry.
here, that gives me the y values. And you see how I just randomly chose the x values? I could have done any values that I liked. I just decided to pick few negatives, few positives, pick 0. But the y value really depended on whatever I chose for x. So this is where the language comes from. We call the x our independent variable. I can do whatever I want, just generate them. And y is the dependent variable here. Y depends on x. I don't know. So x is the independent variable. And y is dependent variable. Y depends on x.
So it's always a function when x is independent.
No.
You got to take none of the x values repeat since you just picked them.
Yeah, but so just the short answer to your question, no. If I go back to equation of a circle, right, I can just generally create a whole bunch of x values, come up with a bunch of y values, but I can do both in that case.
Oh, but -3 and 3 makes it not a function because of the vertical line test, right?
Well, -3 and 3, those are only x, so that's all right. It will pass the vertical line test. Is that what you're asking? Because if I go in -3, 9, -2, 4, -1, 1, 0, and I plot those points, I'll get something like that. If I connect the dots, so it looks like that. Okay? So yes, it passes the vertical line test, whatever it is we talked about last week. And so yeah, from now on, forever and ever, that's the graph of y equals x squared. Okay, so there is a special name for that graph, we call it a parabola. Okay? I mean, but if I go, let's say, to a circle, I'll be able to get different x's given different y's and so forth. So is that good so far? Nothing new? Okay. Now, function notation, and this is the big thing. Because it's kind of inconvenient to us to keep writing y equals x squared, and then we'll have to get all confused about what is the independent, what is the dependent, where do you plug things in. So we're going to introduce a function notation. And the function notation is something like this. That's what we write. So the right-hand side doesn't matter right now. Some kind of an algebraic expression in terms of x. And the way we read this, the left side, we read it as f of x. Where f is just the name of the function. Doesn't do anything but gives the name of the function. And x would be our independent variable. So whatever's in those parentheses, that's the name of the independent variable. How many of you have seen that notation before? So good, most of you? Okay. So whatever it is I wrote before, y equals x squared, now I can just write this. F of x equals x squared. So I have a function, the name of the function is f, the variable is x, and here's the algebraic expression. So this function is up to squaring things. That's the function of that function. Whatever you feed to that function gets squared.
Why is that more convenient than writing y equals x squared?
Well, one of the reasons, let's say before, if I were to ask you, what is the value of y when x equals 3? Okay? So I actually have to say this verbally. What is the value of y when x equals 3? There's no other way for me to communicate my feelings at this moment. Because I feel like evaluating this function at 3. Okay, but now, and this is one of the many reasons, now I can just say, well, what is f of 3? This is equivalent to saying, what is the value of the function when variable equals 3? So all it is, 3, whatever goes in this parenthesis, takes the place of your variable. So that means on the right side, you get 3 squared, which is 9. Okay? So just for the sake of me not saying evaluate this function at x equals 3, I can just write that short statement. So this is how it works. Whatever goes in those little parentheses ends up replacing x in that algebraic expression. Is that all right? So whatever you put in here ends up over there. Okay? So if you want to put -11, -11 gets squared. So that would be, whatever, 121. Is that right? If I ask you what is f of t in this case?
T squared.
T squared. Whatever goes in the little parenthesis after that name of the function replaces your variables. If I ask you what is f of, one of those, you'll say what?
Smiley face squared.
Smiley face squared. That's the notation. Okay? I can ask you things like that. What is f of, let's say, x plus h? When f is x squared. So we're still referring to the same function. See, I called it f, so now, unless I redefine f is for now x squared. So again, whatever goes in here goes in little parentheses. So what is f of x plus h?
X plus h squared.
X plus h squared. Can I extend that?
Yeah.
X squared.
No,
X squared plus h squared.
because x plus h squared means, well, square means multiply by itself. So it shouldn't be different terms.
X plus h times x plus x plus h, I think was taught today.
Who knows the quick formula? We talked about the quick formula. Yeah, x squared plus 2xh plus h. So if you FOIL, that's what you do. So we talked about that when we were doing completing the square.
But which form would you want it? Would you
Um,
want it in the first one?
Yeah, usually the second one, but yeah, you'll be right in either case. Unless I ask you to actually, because you'll be doing more stuff with this. So for the sake of setting this up, you should be alright. Okay? Okay, so here's another example. Here's another example. Let's say g of t equals negative 3t cubed minus, I don't know, 2t plus 1. So I can freely do that. I can just throw a different variable in there. I can call my function g if I wanted to. All it says, g of t does that to t. Okay, you throw in the value for a variable, same thing happens. So just as before, if I ask you what is g of negative 1 is, you would take negative 1, you would plug in for every t in that expression, and then just, compute whatever that is. So what is that going to be? So negative 3 times, what is negative 1 cubed? So it's still negative 1. Someone said plus 2, that's good. Negative times negative, and then plus 1. So what is that? Yeah, so it's 3 plus 3 equals 6. So that's the value of the function. Okay? So that just produced one ordered pair. Negative 1, comma 6. So 6 technically is still the y value if you think from a graphical point. 6 would be the value on the vertical axis, while negative 1 is the value on the horizontal axis. So I can actually think of graphing this specific function. I can just label this axis as t. The horizontal is my independent. Vertical is my dependent. I can just call it g of t. I don't have to call it y. Just g of t. That's the values of the function go on the vertical axis. Right? This is vertical. I always confuse. Okay. Is that good? Okay, good. Now, so there's nothing to it, to this notation. Just for now, it just helps us to plug things in. Let's kind of take that for now. So when we talk about functions, one big thing about functions is finding the domain of the function and the range of the function. And we mentioned that last week. The domain, that's your initial starting point. Those are all the x values. So the domain will be all the independent variables. While range is where you're going, is the y value in the ordered pair. So there's all possible y values. So all the values of the function. Okay, so the domain, all values, well, let me go back. Values is a little vague. Let's say all real numbers the independent variable can be. It's kind of a weird definition, but basically as long as nothing bad happens, we're good. Now, what kind of bad things that can happen to a function? One big bad thing is division by 0. Let's say your function has some kind of a division in it. So make sure your denominator does not turn into 0. Okay, so that's one bad area. Division by 0. Another bad area would be taking square roots of negative numbers. That's kind of a bad thing too for now. Okay? And we'll be adding a few extra bad things that we should avoid. Okay, but for now, division by 0 is kind of the big one.
You mean it's bad?
What? Division by 0? Yeah, it is very
So
bad.
it's not a function.
Well, it's, yeah, I'll show an example, but you can have a function with a division. That's a fine. But whatever turns your denominator into 0 would not be in the domain of the function. So you won't be able to build an ordered pair where the x turns the denominator into 0. It just leads you nowhere. It's nothing happens. While the range, all possible, well, all real numbers. All real numbers dependent variable. Okay. So there are two ways of finding both. There's an analytical way, just looking at the equation, kind of see what happens there. And we can also look at the graph of a function and figure out the domain and range. Okay? Let me give you an example. So finding domain and range using graph. So let's say we have the graph of a function. The graph of the function is given to us. So here's an example. I'm going to give you, I'm just going to randomly sketch a function that starts, let's say, here at -2, and then it just kind of goes on and on and on and on and on and on. Okay, so it keeps rising up as you go. So that's a graph. First of all, we all agree that it's a graph of a function? How do we know that?
Vertical line.
Yeah, vertical line. That's good. Now, again, domain would be all possible x values that are used to build this function. Well, let's see. What do you think?
Greater than -2 or
Yeah, greater than or equal to -2. We do have a point where x is -2, right? And then as x increases, we do get a graph. Nothing below -2. So anything below -2 would not be in the domain of the function, doesn't produce any ordered pairs. So the domain here would be from -2, and we use that bracket to include -2, all the way to a big positive number, so we use infinity to represent that. And it's always a parenthesis around infinity, we cannot include. Okay, just in case.
So you use the bracket as compared to the parentheses.
Right, so the bracket means include.
Well, how come there's a parentheses on the other side? Because it's not a.
Because it never ends.
Yeah, but it never ends, so I cannot just say that it stops somewhere, it just keeps going. But when you see a parenthesis around a number, that means you just don't include that number in
Okay.
your solution. But the bracket means it's part of that set. That's really a set. That interval is a set. We can express this a little differently. Here's a different notation, and you've encountered that notation in your homework 0. So still, I can say the domain using the set notation, and this domain is full of x's such that, you guys said it already, that every x is greater than or equal to -2. So I can just say that. And I'm going to break this notation in pieces. Just write it down, and I'm going to teach you how to say that. So first of all, we've seen those curly brackets. Curly brackets, we use them to represent sets. But in this set, I cannot list all the elements because it's infinite. It goes from -2 and every number from it, so I cannot list them. So when you deal with those infinite sets, that's another way to define a set. First, you introduce a variable that you use to build that set, so whatever, x, t, whatever you like. So I just say this set contains all the x's. This vertical bar, and this is the weird part, you read that vertical bar as such that. That's the math speed. So this set is full of elements such that, and then you put a condition on those elements. So what all those x's have in common, they're all greater than or equal to -2. Because that's what we saw in the graph. Everything greater than or equal to -2 includes that. So here's some kind of a algebraic expression to define what all those x's have.
So what's the point of the first x? In front of the line.
Well, you're just giving a name to the variable. Okay.
So
I could have said t and then t greater than or equal to -2. Because we don't really know what the variable is, right? I haven't labeled it. If I actually went ahead and said, hey, this is x, so then you really have to use x there. But if I said this is t, then you have to use t. But if I haven't, then just do whatever you like. And you've seen that on that homework 0. That popped up here and there, that kind of notation. So just a way to define a set using you know, the inequalities. Now, what about the range of this function? So the range, we just look at the y-axis, basically. That's how you tell the range of a function. So if I look at the y-axis, what is covered on the y-axis? So I'm kind of looking sideways.
0 and greater than 0.
Yeah, so everything greater than or equal to 0, right? The smallest value of y is 0, including 0, right? It's part of it. And then you just keep getting higher and higher and higher. So one way to write that is from 0, and this is the 0. Came out weird. From 0 to infinity. Okay? And again, bracket means we include that. Okay? And again, we can just do something like this. So let's say y's. And again, you're really free to choose any variable. I could have still used x, it wouldn't be a problem. But yeah, so here we go. So it's either one or. So the top one is called the interval notation. That's the interval on the number line. And the bottom one is set notation. Or sometimes it's called set builder notation. Either way. But do you understand how to read it from the graph? Just kind of looking at the graph. So domain is everything on the x, range is everything on the y. Let's do something more fun. How am I guys over here? Okay. So another example. I'm gonna draw something a little scarier. So, is that a function? Sure it is. Can we state domain of that function? What would be the domain of that function? From negative infinity to negative 1, are we going to include negative 1? No, that's what those empty circles mean. We don't include that point. So, from negative infinity to negative 1, are we done? What else? From 1 to infinity, again, not including 1. Now, when I have 2, very good, I see you are showing me the symbol. Have you guys seen that symbol before?
Yeah.
50-50, good, I'll talk about that symbol. For those of you who have seen that symbol, what's that? Union, right? So this is the union. And I'll talk about the union in a second, but really, when you have two separate sets, and you need both of them, you just take the union. It's kind of equivalent of addition, you're just taking both. Okay? So, and I'll do the set builder in a second. Now the range here would be a little easier. What is the range? 0 to infinity, not including 0, right? Because we never really touch the x-axis here. So not including 0 to infinity. Is that okay? All right, so let me talk about this union thing. So we're going back to set theory and set notation. So going back. So when you have two sets, there are really two big operations that we can do on them. You can find the union of the two sets, and we'll be doing that. Or you can find the intersection of the two sets, and we'll be doing that. And I'll just give you a definition of both. So here's first definition. a union of sets A and B, and denoted by this notation. A, kind of a U, but not quite U, B. This is the A union B notation. So the union of sets A and B, denoted by that, is the set of all elements that are in A or in B. And a kind of a big thing here is the word or. That's the key word. When you read a sentence about sets and that word or pops up, it should trigger the union reflex. So if you hear word or, they talk unions, really. That's kind of weird. But and this is, we're going to start arguing about the meaning of the word or in a minute. But that's a good word. So keep in mind, or, that's union. Yeah.
Are we going to be tested on definitions at all?
I don't know.
What is this defining?
That's defining a union. Right? So let me give you an example, really quick example. But you definitely need to know how or connects to union.
Right.
I'm not going to ask, state the definition of union, but you should have that familiarity. Or union. Okay, so here's an example. Let A be this 1, 3, 5, and 7, and let B equal 2, 3, 5, and 6. Here are the two sets. And again, I'm not going to be doing the whole monkey thing because we just need them. Okay, so here are two sets, just randomly generated them. One has 1, 3, 5, 7, the other one 2, 3, 5, 6. So I want to find the union of these two sets. So I'm writing A union B. So now let's really think about what the word or means, because the union is everything that's in A or in B. So I see number 1. Is number 1 is in either A or in B? Yeah, it's in A, so it's good. Has to be in one of them. That's what or. It's either here or there. Okay? And it's not exclusive or. If it's in both, good. If you get at least one number, like for example 3 appears in both, good. We need an union. So basically union, you pile everything together in one big pile. So what do I need?
1, 2, 3, 5, 6, 7.
3, 5, 6, and 7. Sets are repetition free. We don't need to list 3 twice, 5 twice. So if it's there, it goes in the unit. So that's what that or if you think about this, it's either here or there. So then it goes in the unit. Okay? So it's really kind of an addition. It's a set addition, really. And it's putting everything together. So that's what we used here, because I need everything to the left of -1, and I need everything to the right of +1. So I need everything, every number that's here or there, I need it in my solution. Okay, so that's the definition of the union. Definition of intersection. So an intersection of sets A and B and denoted by this kind of an upside down union sign. So when you see a U, that's union. If you see it upside down, that's the intersection. So the rest of the definition is really the same except for one word. The word or, that key word or, will become word and. It has to be here and there at the same time. So everything that both sets share. Here and there. So it's a set. So intersection is a set of all elements that are in A and in B. So they're in A and B at the same time. So the big key word is and. That's the word that we connect to intersection. So or union and intersection. Or in other words, what the two sets share, where they overlap. That's where the word intersection comes from. So if I go back to our original example, A and B, what is the intersection?
3 and 5.
3 and 5. So we're just looking at the elements that they both share. One is in A but not in B, so it's not an intersection. But 3 is in A and in B, so that's in the intersection. So whatever they share, 3 and 5, so that would be the intersection. Okay, does that make sense? So these are the two big things. We'll be using them, we'll need that notation, it'll show up. Okay? So, having said that, if I want to express this domain in the set builder notation, so I'll just say it's full of x's, and now I just need to write a bunch of little algebraic symbols. So, what is the first half? What does that mean? From negative infinity to negative 1. So it's everything that's less than negative 1, right? So I'll just say x is less than negative 1, right? So that's that first parenthesis. What about the second parenthesis?
X is greater than 1.
X is greater than 1. Now, in between, since we had a union, I'm going to write little or. So that's your connection, or union. So if you want to express this in a set builder notation, it's everything that's less than negative 1 or everything that's greater than 1. So that's the whole domain. Okay, so again, union plays well with the word or. How's that? Sure. Fun stuff? Good. How am I online again? How are you guys doing? Can you hear us? Oh, I don't know. Oh, somebody's typing. Yeah, I'm not going to hear you. You're muted. No, you're not muted. Let me mute you. I don't want to hear you. But if you have a question, you can do this. Then I'll probably hear you. Do you have a question? Okay, good. But raise your hand if you do, and we'll stop. What's going on there? Others, I don't know. Okay, sorry about that. All right, cool. So now let's try this. So by looking at the graph, it is easy to find domain and the range. Domain is the x, range is the y. Okay, that's fine. Now, if I give you an expression, if I write something like this, hey, f of x equals x squared. And I can ask you, find the domain of this function and find the range of that function. Okay. Now, when you think about the domain, again, you look for the bad spots, the trouble areas, like division, square roots, and things like that. Well, this is just a friendly squaring process, right? No matter what the number is, you can always square that number, right? Can you think of a number that we are not able to square? Or that would be illegal to square? Yeah, right? I can square whatever you like me to square. So therefore, domain here would be just all real numbers. No matter what x is, I will be able to square that. So domain here, I can just say that, all real numbers. I'll write the symbol for the real numbers. That's one way to say that. Or you can do negative infinity to infinity. That's an integral, entire number. Now, the range is always hard to do algebraically. Without seeing the graph, range is hard. I cannot really think of, I have to think what happens when I start squaring the numbers. In this case, it's probably easy. I know it will never be negative, right? No matter what a number is, if I square it, it's not going to be negative. And, well, what is the smallest value that x squared can be? 0, right? If I square 0, I'll get 0. Everything else will be positive. And I can make it as positive as I like. So what do you think the range here is?
Y is greater than 0.
Greater than or equal to 0, right? From 0 to infinity, including 0. So from 0 to infinity. But we can kind of cheat because we already saw the graph parabola. So everything from 0 to infinity. But if I just write a random looking function, it will be hard to guess the range. Okay? So at some point I will stop asking you find the range of a function without giving you the graph, because it's almost impossible. You really have to get creative. But the domain you can always do. So here's an example. So find the domain. So the domain here would be boom. Oh, I haven't given you a function yet. See, I'm already thinking about domain, but I don't have a function. So let's make one up. Give me some math. X plus 1 over, how about x squared minus 4? That'll be it. All I have to start making it a little interesting. So right away, when you see a fraction, it should trigger a little thing in you saying, oh, okay, division, I have to be careful. Because division by 0 is not allowed, so I have to make sure that my x, whatever the x is, does not turn denominator into 0. So you
If
have
it
to,
does, is there no domain?
well, it's not part of the domain. Because there'll be no ordered pair. Well, give me a number that you think turns denominator into 0. Okay, 2. 2 and negative 2. Good, there are 2. But let's say if x equals 2, right? If I plug it in, it just doesn't give me any output, right? So it does not generate an ordered pair when x is 2 or negative. Right? So those two numbers are excluded from the domain. Everything else is fine. Okay? So one way to do that is to factor this denominator first. That'll be easy for us to realize. This is where you get plus or minus. Earlier we had that confusion. We have a square minus a square. That's what gives you plus or minus. So you can see that the first parenthesis does not work when x equals negative 2. The second parenthesis does not work when x equals positive 2. So it's everything but 2 and negative 2. Everything else works. Okay? So one way to express the domain here would be this notation. So what are all those x's? As long as they don't equal to 2 and negative 2. Right? So I can write that. X does not equal to plus or minus 2. So that's an acceptable notation. So it's everything but those two numbers. Okay?
So that's saying everything except for that?
Yeah, so that's what equal sign with a kind of a, so not equal to, that's what it says. Or if you use the integral notation, they'll get a little trickier, because, let's see, it goes from negative infinity to negative 2, then it stops at negative 2. Right, so it's everything from negative infinity to negative 2. But then again, everything from negative 2 to positive 2. And then again, everything from 2 to infinity, and you have 2 unions. So it's really, it's entire number line with 2 holes, hopefully. Okay, so again, this is the set notation.
Could it ever be not equal to 2 and something else?
Sure, yeah. It could be not equal to 2, 7, 11, and 24. Just
And you would just write like x not equal to 2, comma 7.
Sure,
comma
yeah,
24.
that's fine. And this would be the integral notation.
So, if you get a problem like that, do you try and figure out what would make the domain equal 0?
Denominator equals.
Right.
Yeah. So that's what will make, that's what will cause trouble. When denominator turns into 0, that's when the whole thing is undefined. So we don't want those numbers in our domain. Okay, but if I ask you what is the range of that function, it will not be trivial, right? You cannot just say, well, you know, it's whatever, right? We don't see the range right away. We'll need a graph of sorts to see what the range is. And maybe we can graph this thing. If you have a graphing calculator, that's good. If you do not have a graphing calculator, that's fine. Because there are a bunch of them kind of online. And here's one of them. If I Google mathematical, that first thing that popped up. Visualization toolkit. And I'll just go click. So where is it? Where did it go? Did they take it down? Or maybe it's... Oh, where is that? Here we go. Oh, they took it down. Those bastards. Oh, it just ruins the whole moment. It used to be part of this new applied math department. They threw that whole thing. Well, they're...
How about if you Google online graph?
Yeah, I know, but I don't trust them. This one is good. I don't have time to do this now, but if you own a Windows machine, it does have a graphing calculator as well. But all right, well, if I can probably graph this thing, and you will later as well. We will learn how to graph a function like that. But here is 2, here is -2, here's -1. So probably am I lying to you? What? Okay, I'm lying. Yeah, no, I'm not.
How do you know that it goes in the -1 and not the positive 1?
Oh, that's a secret
Secret.
for now. But I'll teach you that later. We'll talk about graphing rational functions. But let's say you had your calculator, you plugged that function, and then it gave you just started cursing it. That's what your calculator will do if you ask it to graph that function. It'll give you something crazy looking. But let's say you fine-tune your calculator, you change the settings, and it graphed that. What is the range of that function? Yeah, all real numbers. That's just that thing in the middle basically does it, right? It just goes from all the way down to all the way up. So the range here is from -infinity to infinity. And we will learn how to graph. This is what is called rational function because it has a division. We'll learn it in chapter 3 or 4. Okay, good. Let's take a quick break. And I'll pause this recording and we'll come back. Recording. Let me share the desktop again. Okay. Okay, good. Here's another example. And I may be jumping a little bit ahead on this one. But let's say f of x equals the square root of x plus 1. Okay? So now we don't have any division. Division is it's gone. But I have a square root, and we know it's a little shaky when we take square roots of negative numbers, right?
Oh, how do you know it's negative?
Well, I don't know yet, but you know, nothing prevents x from being negative in this case, right? So that's why we're talking about. We don't want that to happen. Okay, we don't want to end up with a square root of -5 because that's not a real number. We want our function to take in a real number and put out a real number. Now, so what do we need to happen? We want the radicand, whatever's under the square root, to remain non-negative. We don't want it to turn negative, right? We have to make sure that the radicand stays non-negative. And the reason why I'm saying non-negative is what is the difference between non-negative and just saying positive?
Anything that would make the entire function.
It doesn't do 0.
Yeah, 0, right? Because non-negative means just no negatives, but positive means just positives, but no 0. Okay? But you can take square root of 0. Square root of 0 is 0. So we just have to make sure, in other words, that x plus 1 stays greater than or equal to 0. As long as x plus 1 stays greater than or equal to 0, we got ourselves a working, well-behaved function. Is that okay? Now, do you remember how to solve inequalities like that?
Kind of.
Just like solving equations, there are a few little tricks, and we'll review them, I think it's in section 1.6. But just for sake of, if this was an equation, how would you proceed?
Subtract 1.
Yeah, subtract 1 from both sides. So x is greater than or equal to -1. Okay? So right there, that's basically the domain. As long as x is greater than or equal to -1, this function will work in a good kind of friendly way. Okay?
But it can't be equal. Oh, wait, no.
Yeah, if it's equal -1, then you get square root of 0, which is fine. Square root of 0 is 0. So the domain here, you can say everything from -1 to infinity, including -1. Or using a set builder notation, which is basically whatever we got here as an answer, only with a few extra ones.
Can you not just say, like, the domain is x is greater than or equal to -1? Is that not?
It's politically incorrect for, you know, it's a little, because again, when you take a test and ask you what is the domain and you leave your answer just saying x is greater than -1, I'm okay with it. Now on your MyMathLab, you have to make sure that they'll specify how they want your answer. They'll say set it as an interval, as a set, or just whatever. You'll know how to put your answer when you're on that online thing. Okay, but on the handwritten, you know, either one of those 3 makes me very happy. Unless you're going for 100%, then I might get picky. You don't know that about me, but I have a very wide gap between 100 and a 99. You can make a lot of silly little things between 100 and a 99. But to get 100 has to be perfect. You should be able to scan it and put it as a solution. But so there's a gap. Anyways, don't worry about it. If we're talking about those types of scores, then we're just wasting time. Good? Domain? Okay. So, now your book goes into 2 or 3 sections talking about equation of the line and linear functions in general. So that's all your slope business. Okay? So I'm going to go through that pretty fast right now. Equation of a line, slope, mx plus b, those things, you know what I'm talking about?
Yep. Ready, set, go.
What? Ready, set, go? You want me to? How much time do I have left? I got about 40 minutes. Oh, man, I can teach this from scratch. I have to. Yeah, that's all right now. Actually, it's a little more. All right, so linear functions. So that basically means the graph of a function is a straight line. Okay, that's about it. Now, when we talk about linear functions, we very rare to say things like f of x equals mx plus b. We just say y equals mx plus b, and we'll just stick to that. But that's basically the idea. You all probably remember what m stands for. Slope. What is slope? What is that?
The rate at which it inclines or declines.
Good. I like the word rate. That's really what slope is. If you're getting paid on a weekly basis, your hourly rate is the slope of the line linear function that represents your paycheck. That's a good example. But yes, rate. Keep that in mind. Slope is really the rate of change of your function. Someone said something else. Rise something. What?
Rise over run.
Rise over run. So all those friendly things. So it's rise over run. It's a change in y. Over change in x. If you have 2 points, that's how we find the slope, right? We subtract the y values. Oh, they all mean the same thing. You know all of those, right? So yes, good. Right? And I'm going to do a few examples. So, but they all mean the same thing. There's a fancy notation, delta y over delta x. Who remembers from, I don't know when, the big capital Greek delta stands for what? Change, right. So instead of writing change in y, I can write delta y. That just means change in y. They're all equivalent, all these things. What is that little b?
X.
The y-intercept, right? So the y-intercept. So the reason why we like our linear functions to be in this form, because it's really easy to graph. Okay, it's really easy to graph linear functions when they are already in a form like that. Okay? So just by looking at this function, f of x equals negative 2/3 x minus 1, what is the slope of that function? Negative 2/3, what does that mean? Down to over 3. So always moving to the right on the x. We'll go up if it's positive, we'll go down if it's negative.
But you always move to the right?
You always move to the right. It's just easy this way. Just move to the right, and then you go either up or down. Or you can go always up and then move left or right, and then just get it. So just always to the right, up or down. Now, -1 is the y-intercept, so I can just go ahead and sketch equation of that line. So -1 is the y-intercept. And then from there, I'm going to go 3 steps to the right and 2 down, or 2 down, 3 to the right, any way you like it. So 2 down, 1, 2, 3 to the right. So here is the map. Well, should be straight. Okay? Happy? Happy. So, mx plus b. So now going back to just the original theories of equation of a line. So we have y equals mx plus b, and this is called slope-intercept form of a line, because, well, it tells us the slope and the intercept. There is a slope-intercept form. There's another one. Y minus y1 equals m times x minus x1. There's another form, there's another equation of the line. Maybe you've seen that. Yeah. What? Yeah, very good. Point slope, because it has a point and it has a slope. We like to call things the way we see them. So this is point slope form. Very good. Point slope form. The way I like to do my equation of the line problems, no matter how you like to do them, you always need 2 things. You need to know the slope of that line, and you need to know any point on it. So always need those 2 things. So when you have a slope and a point, I like to just plug them into that second equation. Because if you have a point, you know x1, you know y1, and you know the slope.
Did you then try and make it into?
Yes, and then you just simplify it till it falls out into mx plus b. Some of you just go straight with x plus b, you kind of plug everything in, you find b separately, and then you go back and substitute. I don't like that. It's too many loops. So I'll just be doing that. I'll just plugging things. So, but again, remember, in order to find the equation of a line, always need two things. And you're usually given, or not usually, you're always given enough information to find those two things. So, to find the equation of a line, we need two things. You need the slope, and you need any point on that.
Any point being
Yeah, just any point on a line, some x1, y1, so anywhere.
But you're not given the slope.
We usually be able to find. But usually, basically, there are four types of problems that you encounter. One, they just give you, hey, here's the slope, here's the point, knock yourself out. Then that's easy. Sometimes they give you, here are 2 points. So use the 2 points to find the slope, and then you do it. Sometimes they tell you, here's the point, and your line is parallel to this other line. And then you have to remember, what do we know about parallel lines and their slopes?
They're the same.
They're the same. Sometimes they tell you, here's the point, and here's the line that you're perpendicular to. Now, what do you remember about perpendicular lines and their slopes? Flip it, and what else?
And then change the sign.
Change the sign. So negative reciprocal. So if one line has a slope 2, then the perpendicular, negative 1/2. Okay? So for example, if I go to this line, negative 2/3 is the slope. Can you tell me the slope of a perpendicular line?
3 seconds.
Yeah, 3/2, right?
Yes.
Positive. So you flip it and you change the sign. So those are perpendicular lines. Negative reciprocal. So that's usually will give you enough information to get a slope. Now there are other 2 little cases when you're dealing with horizontal lines. What is the slope of a horizontal line?
0.
0. And we'll write it all down. And how about vertical line? What's the slope of a vertical line? Doesn't exist, undefined. Because there's no change in x. Division by 0, undefined. Okay? Good. So let's just do a bunch of examples. So find equation of a line. So here's one. Line passes through 1, 2, and the slope m equals negative 3. So here's the point, here's the slope. Can we find the equation? We have everything that we need, right? So the way I like to do this, and I'll do it both ways. I'll do both methods, and you can do whatever you like. They're both correct. So I'm going to use the point slope form. I know x1, that's 1. I know y1, that's 2. I'm reading that from the given point. And I know m is negative 3. So I'm just going to plug everything in. So it is y minus the y value, so 2, equals the slope, which is negative 3, and then x minus the x value. And now I'm going to open up the parentheses and solve for y, and then I'm done. So it is y minus 2 equals negative 3x plus 3, and distribute negative 3, right? And then finally add 2 to both sides. Y equals negative 3x plus 5. Is that okay? Now we can do it the other way. I'll do both. Again, it's up to you the way you like it. I don't care. They both work just fine. If you want to take my word for it in the long run, if this is not your last math class, this one will pay some dividends.
What?
The
Without?
first, yeah, the first method. If you go further in math, if this is not your last class, you will learn to like that method better, the first one. Okay? Now, this is, if you're done, then, really doesn't. It really doesn't matter, just regardless of how many math classes you take. But anyway, so if I do this one, all I know in that equation is the value of m. That's -3. So right now, -3 is given. So this is all I know. But I also know that this line that I'm about to find passes through the point 1, 2. So point 1, 2 is a solution to this equation. So if I plug in 1 for x and 2 for y, this equation has to stay balanced, which means I will be able to solve for b. Okay? So actually substitute x equals 1 and y equals 2. So this is 2 equals -3 times 1 plus b. And then I can solve for b. Right? So 2 equals -3 plus b. So what is b? B equals 5. Now you have to remember to write your answer down. What is the answer? 3x plus. So this is what I don't like about this process, that you have to remember to actually go back and plug everything in. While in the first method, your answer just kind of falls out before you just say it. Again, it's up to you, whichever you like better. I know some of you spend a lot of time just doing the x plus b, so for b, that's fine with me. Still choose the right answer, whichever you like. Which one do you like?
First one.
First one. All right. Are we happy with this? Okay, good. Yeah, let me try something. I'm out of pages. That's all right. Okay. Here's another example. Line passes through -1, 4 and 3, -4. Friend like that. We need 2 things, slope and a point. We have 2 points, no slope. So what's the first thing we need to do?
Plug in the points.
Find the slope, right? So find the slope. So m equals change in y over change in x. In whichever order you do the change doesn't really matter. So if you go -4 minus 4, and then 3 minus -1. You have to watch your signs though. What is the numerator?
Why can't you just plug those
-8.
2 points into the point slope form and then find out what m is?
Excellent question. Because that's exactly what the point slope formula is. It's equation for the slope. Right? Because if you, if I go back here, right? If I divide the left by the x's, I really get m equals change in y over change in x. That's what this formula is. So they're really the same. So yeah, you can do that. So -8 over 4, so -2. Yeah, that's the slope. Now, to find the equation, which point do I pick? Either one. It doesn't matter. Whether you pick the first point or the second point, you still get the same equation. I don't know which one of those is easier. They're both.
I usually try to do the y negative is negative.
You want to do y negative?
Yeah, because if you do y minus negative
Okay.
4 in the y, then it comes out easier for me every time.
That's fine. So what do we have? Slope is -2, and you chose the second point. Okay, let's try the second point. Y minus -4, so you really have to watch your signs. So that's using the second point. Equals -2 and then x minus the x value, which is 3. Okay? And then just simplify that. Y plus 4 equals -2x plus 6 when you distribute -2. And then what?
Add 4.
Or subtract 4? Yeah, subtract 4. Y equals -2x plus 2. Is that okay? Do you want me to do the same thing with the other point? Show that it comes out the same? You got it? Right? I mean, okay, you've done this. This is, if you, yeah, this is, you probably see it. I won't be revisiting it all that much. It's just, it should be common knowledge. Okay, let me have some fun with this. The only way I can make this problem a little more fun, if I say the following: find equation of a line that passes through a point. Oh, that might through did come out. How do you spell through? Like that?
No.
Oh, is that the silly one?
Yeah.
O-U-G-H.
Oh.
O-U-G-H.
Who came up with give me a point.
2, 4.
2, 4. So line passes through 2, 4. And perpendicular to the line 2x minus 3y plus 4 equals 0. Well, why are you smiling? Okay, that's okay. Yeah. So this is 2x minus 3y plus 4. That's another way to express the line, and it's really unfriendly way. It's called standard form, or depending on whichever book you use, it might call the standard form of the line. Whatever. What? That's because that one is an awful way. Okay, good. So yeah. All right. We need two things. We need to know the slope. We need to know the point. We do know the point. We do not know the slope right away, but there are ways to find it, right? So two things. First, we know perpendicular situation here. And now let's write this down. So about parallel lines. Parallel lines, what do we know about the slopes? Same slopes. So the slope of one line equals the slope of the second. M1 equals M2. But perpendicular lines, the ones that form 90-degree angle, the slopes are negative reciprocals of each other. So reciprocal and change the sign. Or you can say M1 equals -1 over M2. So that's the idea. Negative reciprocals of each other. Another way of saying that statement, if you multiply the slopes of two lines that are perpendicular, you always get -1 as the result. That's kind of another way to test. 2 times -1/2 is -1, so we can do that. Okay, good. So, talk to me. How are we going to find the slope of our line that we're looking for? Okay, so what you're suggesting is first, find the slope of that, let's call it reference line. Okay? And we can do that by solving for y, putting into an x plus b form, and just reading whatever the answer is. Okay, so the first step would be to find the slope of this 2x minus 3y fella. Okay? Good. So step 1, so let's call it the reference line. step 1, find the slope of this thing by solving for y. Solving for y. So you suggested move 3y to the other side, which is fine. If I do that, I'll get 2x plus 4 equals 3y. Now what? Divide both sides by 3. Okay? So I want to get y by itself. So we'll divide both sides by 3. We'll get y equals. Now remember, when you're dividing a sum by 3, 3 divides both. But I really don't care what happens with the y-intercept. I just need the slope, right? I know that it's going to be 2/3 x plus don't care. Because I just need the slope. I don't care about the y-intercept of that line. Although it is 3/4. No, 4/3, sorry. Right?
Isn't it negative?
Well, I was talking about the y-intercept, but it doesn't matter. But the slope would be, so what is the slope of this line? So what is the slope of our line?
Negative 3.
Alright, therefore, for our line, m equals -3. Right? So we took the reciprocal and we changed the sign because we knew the lines were perfect. Good? Well, now we can finish the problem. We know the point, 2, 4, we know the slope, -3/2. So we'll just use that point slope form. So m is -3/2, and the point was 2, 4. So plug everything in. Y minus 4 equals -3/2, is it? Times x minus 2. Oh, it's pretty. Gonna come out pretty. Yeah? So we'll simplify this. So y minus 4 equals -3/2 x. And then -3/2 times -2 is positive. Good. 2's cancel. And then add 4 to the other side. Y equals -3/2 x plus 7. Good? Okay. Again, so the last two things that I need to mention here would be the horizontal and vertical. We kind of mentioned that, but let's make it official. So the horizontal lines. So what did you tell me about horizontal lines? So m equals 0. So if m equals 0, the equation is just y equals b. Y is whatever the y-intercept, and it's always that, it's constant. Okay? So to write that in bigger terms, so equation of a horizontal line that passes through point AB is y equals b. Y always stays the same. Y equals that constant. Okay? So, you know, graphically speaking, if this is the point A comma B, and this is the horizontal line, the equation of that line is just y equals b. Y stays the same throughout, no fault. Is that all right? So if I go back to the problem when we had a point 2, 4, what would be the equation of a line that passes through 2, 4, and let's say parallel to the x-axis? Y equals 4. Because parallel to the x-axis is horizontal, so it's whatever the y value stays the same. Y equals 4. Correct. Now, vertical lines. Vertical lines, what about their slopes? Undefined. Vertical lines. Slope is undefined. So the equation is just x stays the same, so the equation of a vertical line that passes through AB is, well, x stays a constant, right? Vertical line, x doesn't change, so the equation is just x equals A. So x stays the same, right? So if I go back to the point 2, 4, the vertical line would be x equals 2, so it just stays the same. How's that? Is that good? Okay, good.
For Sunday.
What?
For Sunday?
For Sunday, yes. Did you just send the class for me there?
Yeah.
Can you not open and close it? You have to like take it all at once. The quiz.
Actually, I don't know. I think you can come back to it later.
Do you have like a time limit on it? No?
This has to be done.
Is it like 10 questions or is it
No,
20?
it's still
It's still like
20.
about 20.
20 questions?
So, and you get 2 shots for the highest score count.
After your first shot, does it tell you which ones you got right and wrong?
I think so. I think if you go back to the grade book, if you click on grade book in my math class, not on campus, but when you were doing the quiz, it'll give you the option to review it.
Okay.
So you'll be able to see what you're getting wrong. And there's also that study plan that will kind of tell you what's going wrong. And, okay. So, so Mary and Amanda, is this thing better than before? This new setup? I don't know if you can hear me. Because I'm kind of far from the mic.